All right, so next we'll have our first lab focus group, and this is Greg Sawicki's lab.
Thanks, Sabrina. So yeah, since last year, the lab's moved to Atlanta. We're now at Georgia Tech. We have a new logo, thanks to our talented graphic artist postdoc in the lab, Emily Abbott. I'm going to first give a few sort of broad philosophical overview slides of how we think about locomotion and how exoskeletons fit into that. And then each of the members of the lab are going to tell you a little bit about what they've been working on for the last, I don't know, 6 or 8 months since we've moved to Atlanta. So we study the physiology of wearable robotics. It's myself, Emily Abbott's a new postdoc, Owen Beck's a new postdoc in the lab who came from UC Boulder, Jordyn, Schoeder, Laksh, Punith, and Pawel, Golyski. There are 3 new graduate students that work in the lab. Our goal is to extract usable principles from the basic biomechanics, neuromechanics, and metabolic energetics of human locomotion and use them to build better devices. We think of these 3 subsystems across kind of a broad multiscalar approach, all the way from whole body down to muscle, tendon units, and muscles, which is kind of where we make our living. That's our bread and butter. We like to think of ourselves as sort of the muscle mechanical response exoskeleton people. Most of the systems we're interested in start out with just biological parts, but then we add some engineered parts into the loop. And like Elliot did a really good job earlier today of describing how those engineered parts can sometimes actually reveal biological principles that we wouldn't have otherwise discovered. All of that stands for physiology of wearable robotics. Simple models is mostly what you're going to hear about today because our lab's not set up yet in Atlanta, so we've been playing around with models a lot lately. Another sort of duality that I like to think about is this idea of top-down versus bottom-up. We spent a lot of time when the lab starting with whole body and trying to wrench down to muscle using things like ultrasound imaging and such. And lately we've been thinking about a bottom-up approach which starts with muscle and then tries to build up from there, understanding emergent properties as they evolve. And that involves some isolated animal preparations, which Emily will tell you a little bit about. So that bottom-up approach starts with muscle. Everyone's seen these block diagrams before, but just to remind you kind of where in this complicated cascading loop of feedbacks we work. Motor commands generate force. Of course, force also depends on the trajectory that the muscle takes. And the first mechanical feedback comes from within the muscle tendon unit. We all know that forces on tendons can modify the state of the muscle. That influences force production. And then, of course, there's the mechanical coupling between a muscle tendon unit and its load and the body. We kind of lump those together. And that's sort of the mechanical domain. And then there's this whole world of sensory feedback, which we're starting to think about as well, which involves modifying motor commands based on the mechanical state of the biomechanical system. In the context of that group of feedback loops, we want to understand how attaching exoskeletal devices, in this case that's just a passive device, takes the state of the body and feeds it back into a parallel force. How do those sorts of devices modify the other feedback loops that I've just described? Okay, so each of the projects that you're about to hear about are going to address some part of this, this block diagram, and with that I'll hand it off to Emily Abbott.
Thanks, Greg. Hi, everyone. I'm Emily. I'm the biologist in the PoWeR lab. And I work with these building blocks of locomotion, the muscles and tendons that move the body in its environment. And in the PoWeR lab, we're all about augmenting locomotion, especially in these unsteady conditions, sort of like a sprint start or jumping. And we think that wearable robotics are great candidates to help people jump over these obstacles. But surprisingly, exoskeletons generally don't use biological design to guide development. And we think that that's too bad because animals are the Olympic champions of working at explosive speeds. And so this is a comparative graph with, on the y-axis is acceleration, and on the x-axis is size. And the unfilled shapes are biological systems, and the filled shapes are engineered systems. And what you can see is that large animals like humans here in blue, and robots don't get to these high explosive speeds that biological systems can. So we want to use wearable robotics to maybe augment the speed that we can work at. Frogs are impressive jumpers, and they use some amplification mechanisms to do some impressive locomotions. And historically, we've understood power amplification at 2 levels. So at the first level is this isolated muscle, and it produces about 300 watts per kilogram muscle mass. And then we can also look at the performance of the whole animal, which is about 1,000 watts per kilogram. This is muscle mass specific to only the muscles producing that movement. And we describe the mechanism of this power amplification as the muscle is in series with a biological spring like a tendon. It's able to contract, store elastic energy by the presence of some sort of catch. And then it can, when that catch is released, it can transfer energy from the elastic element to the body at a rate faster than the muscle can do it. And so that's what we call power amplification. And so you get the most power amplification if that catch is instantaneous, but it's also really unpredictable, and we want to be able to make a more controllable power amplification system. And so the experimental design I'm excited to work on this summer uses a living muscle tendon unit that's attached to a servo motor, and that servo motor is controlled through this biorobotic interface, and that interface would create a simulation of an inertial environment. And we're going to double the muscles and double the servo motors and make this antagonistic pair with that biorobotic interface. And so we will activate both the muscles, they will store energy in their tendons, and then one muscle will be deactivated while the other one is still active. And we think our models indicate that that will enhance power that is transferred to the load. And we'll see if that is the case with real biological muscles. So essentially, we're adding a second muscle into the environment dynamics of that agonist. So stay tuned. We'll see if we can actually produce power amplification. And for more on exos, here's Owen.
Hello. Well, I'm going to do exoskeletons, as you've just heard. Our lab focuses mainly on passive elastic exoskeletons that we really design with the idea of altering how muscles and tendons operate beneath the exoskeleton to augment human performance. And the exoskeleton that I'm going to talk about today is none other than the fancy running shoe that we have shown here. So our story begins with Nike recently came out with these running shoes that have stirred up some controversy. They have reduced the metabolic rate of running by 4% compared to a lot of other high-end running shoes, which is good. It means they're allowing runners to run more economically. And there are a lot of new design iterations with these running shoes. And what my study is going to focus on is this in red highlighted is a carbon fiber plate that these shoes have embedded in their midsole. So previous research has shown that adding carbon fiber plates to the midsoles of running shoes improves the metabolic rate by 1%. And before you shrug off like 1% reduction is small enough, we don't really care about it. In athletics, a 1% improvement in performance actually has like a meaningful result. So it's pretty important. But an interesting thing about these studies is we don't know exactly why carbon fiber plates improve running performance. So that's a question that my research is trying to answer. And we have a hypothesis I'm going to frame using this force-velocity graph. So as muscles produce force, which is seen on the y-axis, velocity on the x-axis, the faster that they shorten, the less force they produce for a given activation. And when you run, your muscles shorten as they produce force on the ground. And previous research in our lab has shown that adding carbon fiber plates to walking shoes slows down your muscles' shortening velocity during walking, indicating you can produce more force for a given activation, making your muscles more economical during walking. And our lab uses ultrasound It's a probe we stick on the back of people's legs and allows us to image how muscles actually move while you walk and run and move about. So we're actually tracking fascicles during running for this study. So the conditions for our study, we have people run barefoot, we have people run in just normal running shoes, and then we had carbon fiber insoles of different thickness and stiffness levels. And we're early in our testing. We've tested 2 people so far. We have net metabolic power on the y-axis, so a lower number is better. It means they're a more economical runner. And if we average our 2 subjects so far, it seems like we're waiting to reveal the story of how carbon fiber plates affect metabolics. But I want to plug, I have a poster where I have the biomechanics from these participants, so I'd love to talk to you about them and see if the biomechanics, I'll tell you later how biomechanics are affected by adding different carbon fiber insoles to the running shoe. And with that, I'll pass it on to Jordyn Schoeder. She's a PhD student in our lab.
Hi everyone, my name is Jordyn Schoeder, and my work focuses on modeling how exoskeletons impact material properties of tendons over long time scales, like weeks, months, and years. While there's been a lot of great advances in both powered and unpowered exoskeletons for metrics like metabolic cost reduction, there is some concern that long-term use of these devices can unload the tendons and the muscles, leading to tissue atrophy, which may cause less economic locomotion, as well as an increased risk of injury. So I'm using modeling to capture how exoskeletons impact tendon material properties like cross-sectional area, Young's modulus, and stiffness over long time scales, as well as to improve our models of tendon adaptation. So this is a relationship for how tendon cross-sectional area and Young's modulus changes with mechanical loading found in the literature. And you can see that there's a dead zone where homeostasis is achieved. Less strains result in tissue loss and more strains result in tissue gain. I incorporate this to my model by setting the dead center of this homeostasis band to a nominal number of cycles of a nominal activity. In my case, I use hopping. Daily locomotion was modeled using a hill-type muscle model with a spring in parallel to represent a passive exoskeleton. Tendon stiffness was fed into the model, strains are outputted, and this relationship is used to update tendon stiffness at the end of each day. And this is run until homeostasis. To account for cycles, I used a sigmoid function to estimate a shift in this relationship, depending on if the person is doing more or less than nominal cycles. So this is a sample result where on the x-axis you can see exoskeleton stiffness as a percentage of normal tendon stiffness, and the y-axis shows the amount of locomotion done throughout the day while wearing an exoskeleton for a nominal number of cycles. You can see that for stiffer exoskeletons worn for longer time periods, there is a reduction in tendon stiffness. However, when cycles are double that of nominal, these tendon losses are diminished, and green shows homeostasis, and there's even several conditions that result in tissue gain. So this might indicate that increasing the number of cycles could be able to compensate for unloading due to an exoskeleton. So for instance, if a exoskeleton reduces someone's metabolic cost and allows them to take more steps throughout the day, they may maintain homeostasis or even gain tissue. While these are preliminary results, and I'm going to be doing human longitudinal studies to improve the relationships for mechanical loading, as well as cyclic sensitivity that I use in my model, preliminary results indicate this to be used as a groundwork for optimization of different parameters for different patient populations, as well as the possibility to use exoskeletons to steer tissue properties and for therapeutic devices. For more on this and more about the relationships that I use, you can come see me at my poster. And up next is a grad student, Laksh, in our lab.
All right, so we just heard about a case where the tendon changes over time. So your body is adapting to the loads and changing over time. But another thing changes over time in the real world, and that's the environment. So in particular, what I'm interested in is what happens if there's an unexpected perturbation in substrate height. So exoskeleton research so far has primarily been interested in the reduction of metabolic cost, and these have been historically achieved by active devices that give you network. But recent advances have shown that completely passive devices can reduce the metabolic cost of walking by 7.2%, and these provide no network. But these studies happen on a treadmill, and that means it's on a flat ground, it's at constant speed, which isn't a good model of the real world. So the question that I want to ask is, do passive exoskeletons destabilize hopping on uneven terrain? And why I say that is, so consider this as a model of a human hopping, right? So you have someone hopping on a platform, and then you suddenly drop it. So the human will probably take 2 or 3 steps and stabilize. Now let's take a spring and see what happens to a spring. If you take a spring and drop it, it'll return back to that same height. So if you have a person with an exoskeleton, and somehow the behavior of that is some linear sum of these two behaviors, and that is, if you're shuttling energy through a system that can't dissipate it, are you potentially destabilizing the person? So to study this, we developed a model of a hill-type muscle tendon unit, which is cyclically stimulated to generate hopping. And this is in parallel with an exoskeleton, a passive exoskeleton that can give no network. And this actuates a mass that's in gravity through a lever arm. We let this come to stable hopping, and then once it's reached stable hopping, we suddenly drop it. And we look at what happens as a function of time and as a function of model parameters. So let's look at the results. The main thing that we are interested in is a parameter called settling time. And this basically says, how many hops does it take for the system to get back to steady hopping after the perturbation? And on the x-axis, you have increasing exoskeleton stiffness, which starts from no exoskeleton to 0.5 times the tendon stiffness. And here you have increasing drop of the substrate height. And what you can see is that as you increase the exoskeleton stiffness, so that's as you go horizontally, you're going more blue, which means your settling time is reducing. What we also see is in terms of peak muscle strain, as you go horizontally, you're again getting more blue. So that means that muscle strain decreases with exoskeleton stiffness. So let's get back to the original question of what motivated passive exoskeletons in the first place. What about metabolics? And as we've seen before, there's a sweet spot for metabolics where if you go higher, you get higher metabolics. If you go lower, you get higher metabolics. And so what this means essentially is that there is a whole slew of solutions where you can get lower metabolic costs than without an exoskeleton, but also lower settling times. And what this means overall is that passive exoskeletons can improve your metabolic costs in steady hopping. It can reduce your muscle injury because your muscle strains are lower, and improve stability on uneven terrain. So to understand how and why this works, you can find me at my poster. And to talk more about perturbations in the context of sensory feedback, I have Paul, who's also a PhD student from our lab.
Thanks, Laksh. Hi, everyone. I'm Paul. And the part of the conceptual block diagram that I'm most interested in is the sensory feedback portion here. So this is where the reflexes live that then change your motor command and then trickle through all these other components, resulting in your end behavior. The specific application that I'm using to address this part of our block diagram is modeling single limb balance on a prosthetic foot. So in older adults, a lower ability to balance on one limb is associated with increased fall risk. And people with unilateral transtibial amputation can rarely balance on just their prosthesis. So putting these two things together, it begins to make sense that people with amputation fall twice as often as older adults. The goal of my project was to explore the interaction of a passive hip exoskeleton with just the stiffness and the absorption of a lateral perturbation. And to address this, I have my model here. So I have a 2-segment model with a head, arms, and trunk, and a leg, with a torsional spring connecting the leg to the ground to represent a passive prosthesis in the frontal plane. We have an impulse applied at the hip joint, and then we have a gluteus medius on both sides to represent the hip musculature. And this gluteus medius also has reflexes built in to help us stabilize the model. And at the hip joint, there's also an exoskeleton stiffness. That's just the torsional stiffness. So here are my results, and let me just orient you to this beautiful graph. So we have perturbation here, increasing. We have feedback gain of a reflex, increasing here. And we have exoskeleton stiffness on the vertical axis. And the color in each of these boxes represents the amount of time it takes to dissipate that initial impulsive energy, where we expect that a lower amount of time to dissipate that impulse is better. So we also have two conditions for failure, where if the ankle torque is too high relative to physiology, that's a failure, and that's the pink. And if the hip angle is more than 90 degrees, that is a fallover failure. So based on this plot, we can see that with increased exoskeleton stiffness and increased reflex feedback gain, the amount of time to dissipate that impulsive energy decreases. So taking these things together, reflexes do in fact influence exoskeleton performance and should absolutely be considered in future design iterations of exoskeletons. And if you want to look at the muscle and tendon level energy analysis, please swing by my poster in room 1212. So here are all of our takeaways. We are Team Orange, so we will be presenting tomorrow. And I'll be happy to take any questions as well as the rest of the lab. Thank you.
All right, so we have 5 or so minutes for questions or discussion. Who wants to start off the question period? Yes, Max?
Owen, hey, so the 1% difference, how do you measure something so small for metabolic cost?
Collect a lot of data.
So that's what they did? You should probably repeat the question if it's microphone. It is not working.
The question is, how do we measure something with such a small effect?
Yes, basically.
You should say what the something is in that case.
Metabolic cost.
The metabolic cost of running was reduced by 1% in previous studies, and the question is how we're going to replicate their finding or find something small. And it'll come out in the numbers. First of all, we have to ask what will happen and collect a lot of data and do a lot of power analyses. If you have a suggestion, but just see what comes out.
I mean, we struggle with it too.
Right.
And like we often, one of the things we want to do, a lot of us want to do, I think, is we want to collect pilot data on one subject and figure out whether or not we've made real differences, which can be small differences, and it can be very, very hard to do, right? And so, yeah, absolutely you can resolve 1% differences, but that might be a couple hundred subjects, right? And you're also changing things about the design of the shoe in order to accomplish that. So I think it's a real challenge in order to
based off the previous data, to say 18 subjects can give us a strong enough power, 80% or a 0.8 power. So we'll see.
Okay.
Not hundreds. Yeah.
Okay.
Allison?
Just one more comment on that. If you do like a fair number of tests, retests within the same subject, or within the same session.
Just a follow-up comment to the question. It's a good one. When you're looking for small differences, I think one of the things that gives us a little more confidence is just doing a lot of retest within the same session. So, 3 repetitions of each condition and looking for consistent trends between the two over the entire duration. It cuts down the number of conditions you can test, but you increase your power that way.
Not in your sensors, but in the body. There can be drift, and so you have to do a lot of comparisons. You want them to be side by side. Now, like it makes it tricky to resolve such small differences. I know you're an expert at it, so for everyone else's benefit, maybe.
Yeah, no, I completely agree, and I think then just you wouldn't do a completely randomized order. I think is one way of starting to manage that.
What are the % differences that you see when you do these repeats on the same subject, same condition? Do you know?
Yes. So I think it really depends on the intervention, right? If you're seeing a 1% change, I don't think you may see on 2 of the trials it looks beneficial, and 1 of the trials it looks, that intervention looks detrimental. There's going to be a fair amount of noise in each of your measurements, and so thinking about, you wouldn't, for that particular subject, like you wouldn't consider each individual trial, you probably would average across all of them. When your differences get bigger, like on the order of like 3 to 6%, like the story becomes a lot clearer.
Okay. Elliot?
This question is for Pawel. Can you talk a little bit about what it means to consider reflexes in exoskeleton design?
Sure. So what comes to mind first for me is hyperreflexivity and stroke. So I could imagine that as a physiological system's gains are increased, that would then change where the optimum may be for the design of an exoskeleton. But yeah, that's kind of my takeaway. Cool.
Okay, next we have a Slack question.
Yeah, this is also for Pawel. Can you consider individual altered hip musculature of amputees in this model?
Can I consider the alternative musculature of amputees in this model?
Yes.
Well, I've got one muscle on both sides that's the same, so I could maybe change the properties of the glute med if they're different between people with and without amputation. But other than that, there isn't really anything else in there to change. So maybe inertia, but.
Great. Thanks to Greg Sawicki's group for a great presentation. Next up.